there are going to be a few just a few variables that I need you to kind of really know that's going to allow you to understand the rest of the lecture, right? So this essentially is all the notation and kind of that you need to know to be able to follow the rest of the lecture. And this should be quite familiar, but maybe the way I presented is hopefully going to solidify some concepts for you. So what I'm going to start out with is thinking of a collection of numbers, and I'm going to call those pxy's, right? And I'm going to have some discrete index set S, right? So S is some discrete set. Could be finite, it could be infinite, right? But the idea is that you can kind of count all of it. It's a discrete set. So, an example of a non-discrete set would be the real numbers, right? But an example of a discrete set could be the rationals, the natural numbers, the integers, right? And so things you can count. And so that's going to be S. And I'm thinking of these numbers with, there are, numbers P, and then they're indexed by the X and the Y, and the X and Y are elements of this discrete set X, right? So I'm just giving you these numbers, and you can kind of pick your own, right? Whether it's a finite collection, infinite collection, kind of picture yourself for yourself. And I'd like these numbers to satisfy a couple of conditions that I'm going to need. And one of them is that pxy is greater than or equal to 0. So every single, and I say each, right? Because I mean for every xy in S, I want that to be true. So each pxy is greater than or equal to 0. And the second condition is that summing up over the second coordinate of P, so summing up over the Z, and keeping X the same, I want that sum to always be 1. And I say each again because that's got to be true for every single X, right? No matter what X I plug in that sum right there, I want that to sum to 1. It shouldn't be too difficult for you to see that 1 and 2 imply this extra third condition, which is that every single pxy, hence I say each, is less than or equal to 1. And if I have a bunch of non-negative numbers and they all sum to 1, if any of them is bigger than 1, it's going to violate the second condition, right? So it's called a proof by contradiction, right? Assume that one of these pxy's violates this condition, say is equal to 2, well then that contradicts item 2 by using the fact that they're all non-negative, right? And so once you have these two conditions, you kind of have this one for free. And so you see right away that these are probabilities, first of all, right? They're between 0 and 1, and so therefore they're valid probabilities. And they're also transition probabilities because of this condition here, and we'll return to it in 1 second. We're going to call these the one-step transition probabilities for a Markov chain. But before any of that, what I want you to understand, kind of the key concept, is that given any collection of such numbers, that generates, or what I call induces, or creates, or just gives us a homogeneous Markov chain on the state space X. Meaning that as soon as you give me the set of numbers satisfying 1 and 2, there, you're kind of creating this probabilistic object. It's called the Markov chain, and it's a process which we're going to call X. It's going to evolve in time, right? K is going to move from 1 to 0 to from 0 to 1 to 2 and so on. And these numbers, pxy's, are going to be called the one-step transition probabilities, right? So pxy is the probability that in one step, X, the chain X, moves from little x to y, right? And the homogeneous part, and this is all in your supplement note, I'm not going to spend time going through it here, the homogeneous part refers to the fact that it doesn't matter at what time you take that one step, right? So this K could be in the wintertime you took a step, and it's still, the probability is pxy, or 0 to 1 could have been summertime. But the point is that in one transition, the probability is always the same, and that's the property of homogeneous chains. Doesn't matter if it's night or day, doesn't matter what season it is, as long as you take one step, the probability with which that move occurs is the same fixed number, pxy, the one-step transition probability from state X to state Y. There's a little bit of notation that I'm going to use later on, and I'll introduce it there also, so you don't have to worry too much about it right now. But whenever you see a subscript here, this is sort of a universal notation for saying that x naught, right? This is a conditional probability that x naught, the initial state of the chain, is equal to x, right? So whenever you see this, just pretend that there is this part appended or inserted right here, right? This conditional. Okay, Um, that's really the main concept, and there's maybe one more thing to be aware of, and that's that these one-step transition probabilities further allow you to define the k-step transition probabilities. So conceptually, this is not a difficult thing, a difficult step to make. All we mean by writing, when we write p xy of k in parentheses like that, all we mean is that the chain x transitions from little x at time 0 to state y at time k, and k can be any integer, right, any time. So that when k is equal to 1, you recover these one-step transition probabilities once again. And so finally, the last thing I want to mention, this is proved in your notes, and I'd like you to kind of make a mental note for yourself to return to the supplement and really try to understand the proof, right? If you can prove this, and the proof is, one way to do so is via induction, you're kind of well on your way to doing a lot of the problems and exercises that we're going to see in this class. So these are a very famous set of equations called the Chapman-Kulmogorov equations, and they have a very nice intuitive, or I guess an intuition behind them. So let's kind of try to explain sort of both sides of this equation. The left one should be clear, right? It says that we're moving from state x to state y, and we took k time steps to do it, right? So we kind of have like a little bit of a road trip, and maybe it's taking k days, and we're moving from some location x to some other location y, and I could even draw that for you here in a second. So let me erase this. The right-hand sum, so as you start kind of reading that equation while I draw this out, essentially is making or splitting your trip into two kind of legs, right? So, there are k days, and suppose that I made a, stop somewhere in the middle. Maybe a better example would be in k hours, right? And so I'm driving and my trip is taking k hours, and what this sum is doing is making me stop or having me stop at some location z, right, somewhere in the middle of my trip, right? So you can think z of as maybe I'm stopping at a gas station, or maybe I'm stopping at some vista point, maybe I'm stopping at some at a fireworks store. I don't know what the examples could be. You can think of your own, but the idea is that I start the trip here, I end the trip here, and the sum is gonna enumerate all the possible stops I could have made, including x and y. Right, so x and y are by definition in the set the state space S, and I'm going to sum over all of them. The second split is going to happen is over time. So this KL, right, these are two numbers that are fixed, right? K is the total hours that I'm going to travel over, that I'm going to drive over, and L is the time at which I'm going to take a little bit of a break and pull over, right? So L is this first kind of initial leg of the trip. And then you can see in these two probabilities, I'm splitting the time into two parts, right? First, I'm going to stop at L, and then I'm going to continue the trip. And the amount of time that I have to finish to get all the way to Y is obviously K minus L. And so what you want to picture here is, some stop Z, right? And I'm stopping over at Z. This is at time L. And the first part of the sum is the probability that I go from X to z in L time units, and then independently of that, right, when you see two probabilities multiplying each other, right, that means it's sort of right, so these are two independent kind of events, right, the journey from here to here, and then independently of that there is a second journey from from z to y in the remaining time, k minus L. Right, so this is a pretty intuitive equation, and you can prove it using induction, and it works for all L less than or equal to k. And it's a pretty good exercise to kind of try to plug in a few values. You should have it work for L equals 0, in fact. You should have it work for L equals 1, when this first part is just a one-step transition probability, right? One step to z, right? And then the rest of the trip, right, the rest k minus 1 hours will be devoted from moving to z back to y. And of course, the z, like I mentioned, the z itself could be an x, right? In which case the trip would have looked like I sort of somehow got lost and circled back to x, and then in the remaining time I made it, hurried up and made it to y. right? So it's a very intuitive equation, especially if you think about it as sort of this road trip with a stop on the way. And the proof, which is in the supplement and also in the book, is a very nice exercise to practice your induction skills on, and there's a couple of other ways you can try to prove it. So certainly worth looking at. But in summary, these are essentially all the kind of this is all the notation we'll need for the rest of the lecture, and we're going to lay out quite a few concepts just with starting with these few sort of simple-minded variables.